Hello and welcome back. First of all, please don't be intimidated by all of the text and drawings that we have on the board. We will be going through everything very slowly, so you're sure that you will get it, and then please make sure you write down any muddiest points that you may have. So recall last lecture, we introduced the fact that there are two different types of acceleration that can be experienced by an object. An object can have its magnitude part of its velocity changed, and it can also have its direction part of its velocity changed. And so therefore we need to be able to distinguish between those two. We can have both accelerations simultaneously, or just one, or none. So the first acceleration is tangential acceleration. It's the acceleration we've been dealing with for quite a while now, but now we need to give it a special name to distinguish it from the other type of acceleration. So tangential, also called linear acceleration, is due to a change in the magnitude part of the velocity divided by time. And the direction that the tangential acceleration points is going to be in the same direction as the velocity at that point if the object is speeding up. And it's going to be opposite to the object's velocity if it is slowing down. Only two different possibilities there for the tangential acceleration. The second type of acceleration that we looked at last video was centripetal acceleration. Centripetal or radial acceleration is due to a change in the direction part of the velocity divided by time. And what direction does it point? Well, it points into the center of the circle that the object is moving through, and we're going to see why that's true today. We also introduced the polar coordinate system, which I know you have seen in your math classes somewhere before. Polar coordinates in two dimensions, use the two coordinates r and theta, r being how far away from the origin the object is, and theta being the angle that the object's location is making with respect to the x-axis. And this coordinate system, r and theta, is useful for describing circular motion. So there'll be times when we want to employ the polar coordinate system, anytime we have circular motion. We also introduced a new quantity called angular velocity or angular speed. Because we aren't worried here about the direction part of omega, then you can interchange velocity and speed. Remember, the difference between these two is direction, but we are not at this level going to concern ourselves with the direction part of omega. So these are analogous here. Omega is the change in angle an object experiences divided by the time it took to change that angle. So delta theta over delta t. We also defined alpha, which is the angular acceleration of the object, and that's equal to the change in angular speed or angular velocity divided by the time over which that angular velocity or angular speed changed. So I've drawn a circle here that shows an object moving in the sense shown by the arrow, and so I looked at the instantaneous velocity at a couple of different points. So you can see at point V1, the instantaneous velocity is pointing into the second quadrant, and at V2 it's pointing right along the negative x-axis. And notice that anywhere along here the velocity instantaneously is tangent to the circle. So the velocity's direction is continually changing by 360 degrees as the object moves through 360 degree rotation. The angle that the object moves through as it moves from position 1 to position 2 is delta theta, and the arc length that it moves through is delta s. The radius of the circle is r. So the direction part of the centripetal acceleration, which we talked about up here, it points into the center of the circle. Let's talk about how we actually prove that that is true. Well, the direction part is going to be the same as the direction part of delta v. Because remember, acceleration is delta v over delta t. So whatever the direction part of delta v is, because delta t has no sign associated with it and no direction associated with it, then the sign for delta V will be the same as the sign for the centripetal acceleration. So I want to find what is the sign for delta V then. And so they're vectors, right? V1 and V2. So I'm taking the final velocity V2 and subtracting the initial velocity V1 to define delta V. And remember, I don't like to memorize how to subtract vectors. I want to only remember how to add vectors. And so I can write then V2 minus V1 as V2 plus a minus V1. And now I'm going to use the tip-to-tail method that we learned back in a few videos ago. So here's V2, and now I'm connecting a minus V1 to the tip of V2. The resultant vector is going to have a tail at the tail of the first vector and a tip at the tip of the second vector. So you can see delta V does indeed point into the center of the circle. So delta V points into center of circle, therefore AC points into center. So they both point into the center of the circle. And so now we've shown that we can find the direction part of the centripetal acceleration. And now let's find the magnitude part of the centripetal acceleration, which we wrote down last time but didn't actually prove. Okay? So we're going to start right here in this box to find the magnitude part of the centripetal acceleration. So recall the arc length formula from back in your math studies. Here's the arc length, the delta S, right? And this angle delta theta that is scanned out for this arc length, the delta S, and this radius of the circle are all related to one another, such that the arc length is equal to the radius of the circle times the angle that is scanned. So this is what we're going to start with, is this arc length formula. Back in your math classes, you probably used L as arc length. Here we're using S, just a different symbol. Now we're going to divide both sides by delta T. So when I divide delta S by delta T, I'm going to have distance over time, and that of course gives me speed. So the speed is going to be equal to delta S over delta T. Dividing this side of the equation by delta T, I'll have R delta theta over delta T. And so delta theta over delta T is our symbol omega. So I can substitute delta theta over delta T as omega. And so now I can write V is equal to R omega. Here it is right here. So this is an important relationship for us. Now, the magnitude part of the centripetal acceleration, we want to consider a very small time delta t, so that delta s is basically a line, not an arc. So this is a very, very small chunk of time. And if it's a small chunk of time, then the velocity v1 and the velocity v2 are going to be the same in magnitude, and so we'll just call them v. So the magnitude of v1 and the magnitude of v2 is just going to be equal to v. So we're going to use similar triangles, and so what we're going to do is take this triangle right here, and remember delta s is basically a line because delta theta has become very small as delta t has become very small. I have to blow it up a little bit so that you can actually see the angle in here. But imagine this now as a straight line. So here is what was my arc length that is now a straight line. Here is the angle delta theta, and here is r. So basically that's this chunk of pi. Delta t shrunk down very small, making delta s a line. Now I'm going to take this relationship between the tangential velocities at the two different points. And so you can see this would be my v2. This is my v2 here. And this is my minus v1. So minus v1, minus v1. But remember, v1 and v2 have the same magnitude, so they're just v. And then delta v is here. Okay, so these two triangles are similar because they share this angle delta theta. As the object moves from point 1 to point 2, it scans out an angle delta theta, and the direction of V1 changes to the direction of V2. So this angle right here is delta theta. So these two triangles are similar. So what we'll do then is write the ratio of opposite to adjacent for both triangles. So delta theta is equal to opposite over adjacent, delta S over R for the left triangle, and delta theta is equal to delta V over V for the triangle on the right side as well. So now just solving for delta V in this square gives us V delta S over R. And lastly, we're just going to divide both sides now by delta T. And when we do, now we have the magnitude of the centripetal acceleration, because delta V over delta T is the magnitude part of the centripetal acceleration. So you can see here that when I divide by delta T on this side, I'm going to have delta S over delta T. That's going to give me another factor of V, so I'm going to have a V squared here, and R in the denominator. So the magnitude part of the centripetal acceleration, V squared on R, the direction part of the centripetal acceleration into the center of the circle. So we'll take this stuff and move forward, defining just a few more quantities for, or a few more relationships for the circular motion next time.